Okay, so in the earlier class we saw that if you have a nonlinear relationship between current and potential, when you apply a sinusoidal potential you will get higher harmonics also. You will get the response at fundamental and you will also get response at higher harmonics. Then we moved on to FFT and digital filter, a particular filter called FreeZ in MATLAB. And with few examples we saw that if you have more number of points per cycle you can get higher harmonics, and if you have longer duration you will get higher resolution. So, frequency resolution will be better if you have a longer duration of data acquisition. What I want to show today is to look at multi-sine, that is when you add multiple sine waves together and apply it, you can get the response, you can do FFT and get the impedance at multiple frequencies simultaneously. But what are the pitfalls in doing this, or what are the aspects that one needs to know before applying? Okay. There are different choices one has. One is to apply sine waves with harmonics, that is I can apply a sine wave at 1 Hz, 2 Hz, 5 Hz, 7 Hz and combine them together and apply as a one wave, that is a choice. I can say 1, 3, 5, 7, these are odd harmonics, I can mix in any way I want. Another choice is to mix waves with different frequencies where the frequencies are not harmonics. So, I can say 1, 1.5, 4.75, whatever number I want I can choose those frequencies, create waves and apply. In addition, I can give different amplitudes for each wave. I can also give the phase, that starting phase to be 0 or something else, whatever I want I can choose that. Okay. And each one of this has an implication. When you apply a multi-sine using a commercial software, by and large you will not know what it does. At the best you would know these are the frequencies at which it is applying this. Beyond this you would not know, okay. But you should know at least what the implications are. So, I want to show you what happens when you use harmonics. Odd harmonics is one choice that is proposed by few and it is used at least in one commercial machine, if I remember right. Non-harmonics are also used. Non-harmonic meaning they are not integer multiples of the base frequency. Crest factor is a parameter that one should know. It decides whether nonlinear effect may manifest or may show up in the result or may not show up in the result. Okay. And when you use non-harmonics, there is a problem. You will have some problem in the measured values, you will have some problem in analyzing the measured values and extracting the impedance correctly at those frequencies. Okay. So, I want to discuss those also, and if we have time we will start with data validation. Once you get impedance data, you have frequency, magnitude and phase, that is one way. You may have frequency, real and imaginary part. You will have 3 columns in, let us say in Microsoft Excel. If you have a data set, it is possible to do some consistency check to know whether this data has come from a clean system. Okay. What do we mean by a clean system? We will come to that little later, but it is possible to do this. So, we will also see what are the methods of doing this data validation. So, first we will take a simple case where you have 2 sine waves, one is at 1 Hz, another is at 2 Hz. 2 Hz means you have 2 sine waves in 1 second, in 3 seconds you have got 6 sine waves, in 3 seconds you have got 3 sine waves here. Starting phase is same, it is 0 for both, they have equal amplitude, goes from 0 to 2, 0 to 2. If you add them together, it does not go from 0 to 4 because the maximum occurs at one time here, it maximum occurs at a different time here, but you can see it is a combined wave and this has a period of 1 second, meaning after 1 second it repeats. If you give the data from 0 to 1 second and then say copy this, you would be able to generate the full wave. If I take this combined wave and subject this to Fourier transform, assuming I have enough number of points given to this data, okay, I have just given you a continuous line here, but I would actually give data at equal intervals, and if I give enough number of data I can get many number of harmonics. I definitely give at least one cycle, I will probably give few cycles, I can get data at 0, 1, 2, 3 and more, but I am just showing you 0 to 3 and you see that magnitude is 2 at 1 and 2 Hz, everywhere else it is 0, phase is 0 here and these values you can ignore because the magnitude is 0 anyway. So, this is just to show that you would get the correct values by subjecting it to actually digital filter. In this example I I have used frequency here. If you use FFT also, you will get the same result. So, if you combine 1 Hertz and 2 Hertz and sample it up to 1 second or 2 or 3 seconds and give this, you will not have any problem in retrieving the magnitude and phase of the input wave. Output wave, that is the current wave, if you do the same thing, you would get the correct result. This assumes that the cycle stabilization time is 0. If it stabilizes after some time, we will just assume that we are taking the data after stabilization and then subjecting that current to Fourier transform, and you will get these results. Does it make sense? Potential, when we apply, we are the ones who are controlling it, so we can make sure that these potential values are correct and they are steady periodic. When the response comes, it may take some time to give a steady periodic value. We have seen that before, that it will oscillate and stabilize after some time. So, if you take the data in the beginning and do Fourier transform, whether it is a single sign or multiple sign, you will have problem in getting the correct impedance values. If you take the response after it stabilizes, then if the Fourier transform is done correctly and if the samplings are done correctly, you will get the correct value. How does it come? You are asking, how does it come here or how does it come this way here? Top right. Add these points together, that is all you need to do. Meaning, here I have generated this wave by taking time intervals of t 0, I will just make up this number and say 0.1 second, 0.2 second, 0.3 seconds and so on. Okay. Now, the first wave is generated using 2 sine 2 pi f t plus 0, f is 1 Hertz. At various time intervals, I know the wave 1 will have these values. Y2 is going to be 2 sine 2 pi, f here is 2 t plus 0, and the y here is going to be y1 plus y2. Here I have shown it as a continuous line. That means I have given data points at fine grid and asked MATLAB to plot it as a continuous line, but actually this is made up of discrete points. You want to know how the addition of these two comes to this? You can try it in any software, you will find it. Okay. So, you can do this with the different phases, correct. I have given 0 phase in this example, you can give another phase value. One of the values typically will choose it as 0, the first wave typically we choose it as 0, you can choose any value for this, it is fine. Now, this is wave 1 with 1 Hertz and 45 degree offset, phase offset. Second wave is with 90 degree phase offset, but then you can generate this, you would get a combined wave which looks like this. Here also after 1 second the cycle repeats. So, what it means is the period of the combined wave, it does not change with the phase, it does not change with the amplitude of each wave, IAC 01, EAC 02. Here the example is with 2 waves, you can combine many waves. The total period of the combined wave will not depend on the phase or the amplitude, it will depend on the frequency. And when you have harmonics, whether it is odd harmonic or in general any harmonic, this we call as base frequency, and the subsequent frequencies are generated based on this number. So, I have 1 Hertz, 2, 3, 4, I can choose any of those. The combined wave will have the frequency of the base frequency. I can choose this as 0.1, then this is going to be 0.2. I can choose this as 1 millihertz, this is going to be 2 millihertz. As long as the second, third and remaining waves are integer multiples, the frequencies of the remaining waves are integer multiples of the base frequency, as long as they are harmonics, the combined wave will have the same period as the first wave. And of course, this is just to show that if you do the Fourier transform or digital filtration, you will get the values as magnitude of 1 here, magnitude of 2 here, comes out correctly. The phase value, this is 45 degree, this is 90 degree. You can try varying it, obviously it will work as long as the input to this filter is correct. Now, I want to look at non-harmonic inputs. Fourier transform basically tells you at these frequencies, these are the amplitudes and phases. You can call it as deconvolution. See, the wave here is a mix up of these two waves. Out here of course, it looks relatively simple, but if somebody just gives you this wave or gives me this wave and asks me, this seems to be comprised of multiple waves, can you tell me What it contains, I can't tell upfront by looking at this that this is a wave which comprises of 1 hertz and 2 hertz sine waves with 45 degree and 90 degree. I can call this as a sine wave with 90 degree, I can call this as a cosine wave with magnitude of 2 for the second wave, magnitude of 1 for the first wave. I can't look at this graph and tell this, whereas look at the first graph alone on the top left. You can see, yeah, it looks like a sine or cosine whichever way you want, but it has a period of 1, it has a magnitude of or amplitude of 1. I can think it is a sine wave with 45 degree offset. I can think of it as a cosine wave with minus 45 degree offset. So, looking at the individual components, one can say what this is. Looking at the combined wave, it is not that easy, and this is a clean example with 2 waves. If you have multiple waves, it is just not possible. The best thing you can say is it is a periodic wave with this period, that is all you can say. Fourier transform helps us decouple this and get it into sine waves of various frequencies with the corresponding magnitude and phase. Of course, it comes out neatly because the input waves are sinusoidal. If the input waves are not sinusoidal, they are periodic but a different waveform such as triangular wave. Fourier transform will give you frequencies, many frequencies with varying amplitude and varying phases. If this comprises of rectangular waves like what we have seen before, pulse, this is also periodic. I can say starts here, goes up to this and then it repeats. Again I will get many frequencies, in theory infinite number of frequencies, in practice few frequencies. So, multiple sine waves with different amplitudes and phases, when you add them together you will get the pulse wave. But here, because we apply multiple sine waves, it is clean in the Fourier space. If I look at 1 hertz and 1.5 hertz, 1 hertz means 1 second I got one full wave, 1.5 hertz means in 1 second I got 1.5 wave, 2 seconds I have 3 waves. So, the time period for the second wave is 1 divided by 1.5 seconds, that is 2 by 3, which is 0.6666 and so on, you can say 0.67 as a truncation. Now, the thing is this, if I combine them, and these are with 0 phases, right, if I combine them, the combined wave has a period which is 2 seconds. So, I can apply this wave, I can get the result in 1 second, assuming that I can supply 1 cycle, take the result. Here I can supply 1 cycle and that is going to take me 0.667 second, I will wait for 0.68 seconds. So, if I apply this wave, get the impedance, apply the second wave, get the impedance, I still take only 1.68 seconds. I apply the combined wave, I need to wait for 2 seconds for the combined wave to come like this. So, what it means is the period of the combined wave, which is 2 seconds here, is longer than the period of the individual components. Earlier case, I can take this data in 1 second, I can take this data in half second, I can take the combined data still in 1 second. So, this is all that limits the time period. None of the remaining will add more time to the data acquisition time. When you have harmonic waves, you can look at the base frequency and decide the time period, and that is the time period necessary for the entire set measurement. When you look at non-harmonics, you will need longer time than just the base. So, how do we calculate the total period of the combined wave when this is not harmonic? So, you have to write the frequency ratio. Right now I can write it as 1.5 by 1 or I can write it as 1 divided by 1.5 and make it as the ratio of 2 integers. So, frequency ratio f2 by f1 3 by 2, multiply the frequency with the integer, that would tell you how long you have to. Same procedure is described slightly differently here. Find the period of each wave, you have 1 second here, you have 0.667 seconds here. Find the minimum integer multiple, that is I need to multiply this by 2, this by 3, then the value 1 into 2 gives me 2, 3 divided by 1.5 gives me 2. So, that means In 2 seconds the first one will complete 2 cycles, second wave will complete 3 cycles, then you can replicate them. If I truncate it at any intermediate value, I will not have completed a full cycle for at least one of these waves. So, find the minimum integer multiplier for each period, so that the product, that is the integer and the period, is the same for all of this. So, instead of 1 and 1.5, let us take another example where we add 3 waves with 1 hertz, 1.8 and 2 hertz. You can see the period of 1 hertz is 1 second, period of 2 hertz is in fact half second. This is going to be less than 1 second anyway. So, if I do this measurement, I can do the first measurement in 1 second, second measurement in less than 1 second, I will just say 1 second, third measurement in half second. So, 2.5 seconds, 3 seconds I am done. Apply the sine wave, get the data, apply the second sine wave, get the data, apply the third sine wave, get the data. Here we are ignoring the part where we have to wait. It is to say that wait time is pretty much 0, but if I combine the wave, I need to have 5 seconds to get the wave to repeat itself. That is the period of the combined wave. So, I would write 1, 1.8 and 2 as 9 by 5, 2 by 1, and I have to multiply 5 into 1, 9 divided by 1.8, but I would get the total period as 5 seconds. If the number, if I had to combine 1 hertz and 1.01 hertz, 1 hertz I will take 1 second, 1.01 I will take close to 1 second. If I combine these two, I will have to wait for a really long time for this wave to repeat. That is, after 1 cycle it will be slightly off, after 2 cycles it is going to be little bit more off, after 3 cycles, after 100 cycles or 101 cycles, after many cycles you would find that they are repeating. So, after many cycles the 1 hertz would have taken some number of cycles, 1.01 would have taken one less number of cycle, and then you can say from here to here you take this and then copy this, you will get the same wave. That means when you combine waves which have frequencies, non-integer frequencies, combined wave will take much more longer period compared to the original wave. So, when you have long acquisition time, multisign is not advantageous. The reason we want to use multisign is because it will take shorter time compared to doing the individual sine waves. But if the combination looks like it will take longer time, there is no point in doing the multisign. That means if you have harmonics, multisign will not take longer time, maybe that is a good choice. If you have non-harmonics, it is not a good choice. That is what this tells us. There is another factor or parameter that one needs to look into, it is called crest factor. Yeah. So, this is just a mathematical representation of adding different sine waves. Let us take sine wave 1 to n, 1 to 5, 1 to 10. This is the amplitude of the first sine wave, second sine wave and so on, with the corresponding frequency and phase. Crest factor is when you look at the combined wave, what is the maximum? Maximum divide by the RMS value, root mean square value. If you take a pure sine wave, maximum divide by the RMS value is going to be square root of 2. If you combine the sine waves, the maximum divide by RMS will not be square root of 2, it will be more than that. You can optimize the crest factor by adjusting the phase. RMS value will not change, but the peak value can change. There are different choices for the phase values. One choice is to use 0 phase, meaning do not give phase for any of the input values. That is mathematically simple, or implementation wise it is simple. Another is to give random phase. So, some of the publications suggest using random phase for this. Now that you have good optimization software, you have access to the software, it is possible to give optimized phase for a given set of sine waves with certain amplitude and frequency. If you tell I want to add these sine waves, these are the amplitudes I want to give, these are the frequencies I want to give, then you can do optimization for the phase values. You change the frequency or the amplitude, this phase value which gives you the lowest crest factor will change. We want a low crest factor. We want a low crest factor because when the crest factor is high, it is effectively going into the nonlinear regime. Now, if you use odd harmonic waves, odd harmonic meaning 1, 3, 5, 7 etc. for the frequencies, there is a formula called Schroeder phase which tells that if you generate the phases like this, first phase choose it arbitrarily, second phase onwards you can estimate it using this formula where A here is the amplitude and this is meant for set of cosine waves, but you can choose the first wave to be with the phase of 90 degree it becomes a sine wave, or minus 90 degree it can become sine wave. Okay. You can generate this. This is not going to be optimal, but this is going to be better than 0 phase. So, suggestion is this is close to optimal. If you want optimal phases, there is no analytical formula to calculate it as of now. It has to be done using numerical method. But analytical formula, if you have it, it is lot faster to generate these phases. So, at least I think one company uses the Schroeder phase with odd harmonic, the commercial one. If you have n number of waves, or here f number of waves, you can use this formula to calculate k equal to 1 to f, and you can generate the waves from this. This works reasonably well when you combine waves 1, 3, 5, 7, 9. When you combine waves with this odd harmonics complete set, meaning if I want to go from 1 to 13, I should take the full set. I can't just say I want only few waves. This is odd harmonic, fine, but if I take this set, use this formula and get the phase, I may not get good crest factor. So, be careful when you read literature and use that information. They may not tell you that this will not work if you do not have a complete set. They will say if you use odd harmonic, this seems to be a good suggestion. It is not the best case, but it is actually fairly good case. You should evaluate it yourself and make sure that it works well for your case. So, this example, if I use 0 phase, I put 1, 2, 3, 4, 5, base frequency is 0.1, I have combined waves which are 0.1, 0.2, 0.3, 0.4, 0.5, each one with 10 millivolts, I get a nice wave which looks symmetric, period of 10 seconds, base frequency is 0.1, so period is 10 seconds, the remaining are all harmonics, therefore, the combined wave also has a period of 10 seconds. The crest factor is 2.5. So, if you look at the peak versus RMS, it is going to be 2.5. You can calculate it and find it. For now, I have 5 waves in this, each one of them is 10 millivolt, 10 millivolt is the amplitude. The signal to noise ratio at each frequency depends on the amplitude of that input wave at that frequency, also depends on the amplitude of the noise. Noise level is high, everywhere you will get poor signal. It also depends on number of cycles averaged. What do I mean by that? This wave contains 5 waves, correct. Now, it contains 5 hertz, meaning in 1 second 1, 2, 3, 4, 5 cycles of 5 hertz with 10 millivolt amplitude is used here. I use only 1 cycle of 1 hertz, same 10 millivolt amplitude is given here. If I use many cycles at a given frequency and take the Fourier transform, the signal to noise ratio will be better. So, although this is a combined wave with 5 frequencies, if I assume that the noise level, noise floor is same at all frequencies, then I will get a better quality data at 5 hertz, I will get relatively poorer quality data at 1 hertz, because the combined wave essentially uses 1 cycle of 1 hertz and 5 cycle of 5 hertz. Again, does it make sense? No? Yes? Okay. See, if I take data, forget about the combined wave multi-sign, just take data for 1 cycle. In ideal case, you have 0 noise. So, you take 1 cycle, do Fourier transform, you will get what I showed you in the earlier graphs, nice magnitude and phase. In real life, you are going to have little bit of noise. If you take 1 cycle, it will give you the magnitude and phase, but they will not be good precise number, they will be little bit off. If I take multiple cycles with the same noise level, the Fourier transform will reject the noise better when you have much more number of cycles. I should not say it rejects the noise better. The signal strength at this frequency will be good compared to the noise. Noise will have amplitude at all frequencies. When we average over many cycles, you will get better quality data, meaning it will come closer to the actual value. Now, you can say for any wave, if I take 1 cycle versus I take n number of cycles, the data quality is better with n number of cycles when you average over this n number of cycles. Even without the sine waves, just imagine you have a constant, you are expecting a constant signal, the system actually gives you a constant signal. This is 0, whatever this is the signal, it is supposed to be a straight line. But in measurement there is some noise, therefore it looks like this. The noise is going to have certain amplitude and it is going to be plus or minus some number on the average. If you take data over long period and then average the values, you will definitely get a better average compared to taking data over a small period. If you take a number of data points, that is one, and second you can also take data, I can take data like this, I can take data at all intermediate values, I take more number of samples and average them, I will get a better average. Likewise, if you do Fourier transform of a data which contains multiple cycles at a particular frequency, you are likely to get better quality data. But because the combined wave here contains 5 frequencies in this example, the 5 hertz has 5 cycles here, 1 hertz has only 1 cycle here. So, in theory when there is 0 noise, I will get clean output from this. In practice when there is a noise, I will get a response saying this is the magnitude versus function of frequency in the Fourier space. I will get some value 1, 2, 3, 4, 5 hertz here. The quality of data here versus the quality of data here, in general this is going to be better. So, I will not get the same quality data. One way to adjust for this is to give larger amplitude here compared to the amplitude here. So, you do not want to necessarily give equal amplitude to all this. For us to understand, for illustration I have given equal amplitude and added them here, but that may not be the best way. You may want to give larger amplitude at the lower frequency, so that the signal to noise ratio is better here. Number of cycle averaged is more for the higher frequency. So, in general you want equally good quality data everywhere. So, the point here being, when you do single sign, usually you will apply same amplitude everywhere, okay. You will get more cycles averaged at very high frequency. At the medium and low frequency you will probably have few cycles, but the data you get out of that versus the data you get out of multi-sign may not always match, because there are a lot of things that are different in the multi-sign versus single sign. If you take a electrical circuit dummy circuit board, you will probably get similar data whether it is a single sign or multi-sign, and you will get it faster in the multi-sign. It does not mean in actual electrochemical system you will get equally good quality data or same data at a shorter time. If I change the phase value, this is an example where I have used odd harmonics 1, 3, 5, 7, 9. 0 phase you get a wave, obviously it is periodic at 10, I had probably just truncated one point before that, so that I could give it to Fourier transform, and 0 phase has a crest factor of 2.3. Schroeder phase, the wave looks ugly, ugly meaning compared to this, at least it appears ugly to me, okay. Looking at this you can say it is nice periodic wave, this is also nice periodic wave, it just does not appear so to us, okay. It has a different phase and the crest factor is lower. That means it goes up to whatever 35 millivolts here, it goes only up to 30 millivolts here roughly. That means from the steady state we move it up and down when we apply sinusoidal wave. On the left side that graph goes more compared to the right side. So, that is effectively saying EAC0 on the left side is higher compared to the value at the right side. Now, I also want to show what happens when you use random phase. Random number generation, each time it will give you a different set of numbers. In one case I got 1.83, which is actually good, better than Schroeder. One case I got 2.59, which is worse than 0 phase. So, random phase generation, depending on your luck, it may give poor or large value of the crest factor. When the crest factor is large, it basically means you are going into the nonlinear regime, which means you will get higher harmonics. System is nonlinear anyway, but if you apply large amplitude you will get higher harmonics. If you apply small amplitude we will get higher harmonics, we can neglect them, they are small. Now, I want to show you another example. where it is odd harmonic, but it is not a complete set. I want to go from 1 to 9, but I am not taking all the odd frequencies in between, I am taking 1, 3 and 9, I am skipping 5 and 7. 0 phase is actually better than Schroeder. In terms of the crest factor, this crest factor is 2, this is 1.86. So, do not always assume that if you have odd harmonic, Schroeder phase will give you better crest factor compared to 0 phase or random phase. So, if you use the full set, it is okay. If you use partial set, you are better off using an optimization program to get the phase values and calculate the multiple sine wave. Now, one advantage in using the odd harmonic is if I supply the wave at 1 hertz, 3 hertz, 5 hertz, 7 hertz, I can also look at the values when I do the Fourier transform. Definitely I will have enough number of points and enough duration to get all the even harmonics also, and if the nonlinearity shows up here, 1 hertz will give me a data at 2 hertz also, 3 will give me a data at 6 hertz also. So, I can look at it and say, okay, I seem to be in the nonlinear regime. So, I should redo this experiment, maybe I can change the phase, optimize the phase, but there is only so much you can do in terms of optimization. You want a good signal to noise ratio at each 1, 3, 5, 7 frequencies, which means you need to give a minimum amplitude, you can't give very low amplitude. If you give certain amplitude, no matter how much you optimize, the crest factor is going to add up, it is not going to be 1.4, it is going to be higher than that. So, you can't completely avoid nonlinear effect. All that you can get from this is to know whether it is present or not. If it is present, you can try optimizing the phase, but beyond a limit you cannot optimize, and then you will have to say I have to reduce and accept a poor signal to noise ratio. There is another problem. Each decade, meaning 1 to 10, 10 to 100, I have only 5 choice, 1, 3, 5, 7, 9. I can say I will take frequency of 0.1 hertz, 0.3, 0.5, 0.7, 0.9. Then next I will start again at 1, although it is close to 0.9, it is fine, 1, 3, 5, 7, 9, 10, 10, 30, 50, 70, 90 and so on. Because I choose odd harmonics, I have only 5 points per decade. If I also apply even harmonic, I cannot tell whether nonlinear effect is present or not, because I apply input at 1 hertz, I apply input at 2 hertz, I will get signal at 1, 2, 3 and so on. So, I can't say whether nonlinear effect is present or not, so I can't use that. What happens when you use these frequencies? This left side is log space frequency, same number of points per decade, meaning it is 1 hertz, maybe 1.5, we can see the numbers later, multiply 1.5 square and so on. 6th point is 10 hertz, it is not 1.5, it is going to be a different fraction, but I can divide this into geometric series, I can divide the space of 1 to 10 in a geometric series and get these frequencies. If I do this with the odd harmonic, this is what I get. This is 10 power 1, this first fundamental is 1, base frequency is 1, 3, 5, 7, 9, 10 comes close to this, the gap between 1 and 3 is large, 10 and 30 is, or this is 100 and 300, 300 to 500, 500 to 700 to 900, 900 to 1000 is very close in the log space. So, if I look at this graph, this is a neat graph, I have used this to simulate the impedance for the Randall circuit that we have seen before. If you have noise, it is not easy to figure out how this shape is going to be. Same way, you can look at the phase values, you see large gaps in the data, in the abscissa, x axis. Here I have taken 3 points or 5 points per decade, I can take 7 points per decade, 10 points per decade. What it means is I will get data in a close packed curve, and 1 or 2 data points occasionally will go off the chart. I can delete them and say there is some problem during that data acquisition, maybe some noise was there, remaining data I will take it. Here already you are in a sparsely spaced region, you throw away 2 data points, then you will have to really guess what is happening in between. So, from that perspective, odd harmonic choice is not really a good choice, and if you skip some of the frequencies 1, 3, 5, 7, 9, if you skip, it is going to be worse. So, here is just an example. If I want in real log space 5 frequencies per decade. I have one, this is the geometric series, it is 1.58, 4893. You do not have to use it this way, you can use it, truncate it at 1.58, second can be 2.51, 3.98, 6.31, next is going to be 10. You can do 7 frequencies per decade, 6 frequencies, 10 frequencies per decade, and of course you have to truncate it at few decimal places. But the problem is when you combine these waves, if you take them as single sign, there is no problem at all. If you combine these waves, the period of the combined wave is going to be very, very long, because these are not integer multiple of the base frequency. If you take more decimals, it is going to be extremely long. If you take fewer decimals, I can take 1.6, 2.5, 4, 6.3, that is probably the best I can do. Here I will have to at least take 2 decimals so that it looks little different. I can't take 1 decimal and do this, it won't be that good. So either I have to wait for a very long period, or I will combine the waves, but I won't wait that long, I will chop it off in between and replicate. In the time domain, I know it becomes a periodic wave after a long time, but I do not want that. I think after, I have 1 hertz, I have 10 hertz, I have 1.58, 2.5. So 1 hertz gives 1 cycle in 1 second. Maybe I wait for 5 seconds, I will have 5 cycles here, I will have a non-integer value here, but I will have enough number of cycles, so probably it is okay, I can average out. But it leads to certain problems. There are different problems. One is called aliasing, another is called spectral leakage. Aliasing, I want to show one example here. Let us say you have a signal which is given by the, I think I have not given it correctly, but it is alright. The legend is not correct. The brown color wave is high frequency wave. This is 1.1 hertz. In 10 seconds, I have 11 waves there. Now, I do not sample it very nicely. I mean, in this impedance case, we know what wave we are applying, so we will sample it nicely. But let us say you are taking data from some random source. We sample it every second. You got data here and so on. If I fit this to a sine wave, it will say this fits nicely to a sine wave of 0.1 hertz frequency. So, the blue color is actually 0.1, brown color is 1.1. So, I will get a clean fit. It will give me a phase, it will give me an amplitude, and it will tell this frequency, at this frequency you have the results, but it is not a correct result. We are not sampling it fast enough, and because of that what we should get as 1.1 hertz has come to 0.1 hertz, and we will think it is clean. If I actually fit a sine wave, it will fit nicely. So, this is one type of problem. So, different signals are not distinguishable. Okay, that is due to poor sampling. You can increase the sampling rate and you will find that this is not at 0.1 hertz. Spectral leakage, we expect that it has to go to this frequency 1 hertz, 2 hertz, etc., and it goes to other frequency, the power leaks to other frequencies, that is called spectral leakage. When we write the spectrum, meaning in magnitude and phase as a function of frequency, it goes to other frequencies. So, in this example, if I take 2 samples 1.25 and 1.5 hertz, combined wave actually you have to wait for 4 seconds. This individual wave you have to wait for less than 1 second. And I say, okay, this 4 seconds I do not want to wait, it is too long. I will take it up to 2 seconds. Anyway, I have more than 1 cycle here, chop it off at this level and then replicate it. So, I take this graph, chop it out 3 seconds, 2 seconds, one of those values. In this example, I have shown at 3 seconds. Say I would definitely have 2 cycles of this, more than 2 cycles of this. Let us see what we get. I am expecting magnitude of 2. Instead, some of it has gone to DC, some of it has gone to 3 hertz. So, the power has leaked from 1 hertz, 1.25 and 1.5 and moved away to 0 and 3. These are 0 phases. Phase has gone all over the map. So, I can't chop it off. I have to give full wave. I can chop it off with a trick called windowing. We will continue with that in the next class.